Now that you know when to evaluate realistic closure times in non-return valves, what are the consequences of finite valve closure times in tangible terms? First, let me highlight the situations where significant non-return valve slamming is likely to occur. 1. In pumping systems with very high static lift. In these cases, the water column alone can eventually generate substantial reverse flow conditions. 2. When pressurized air vessels are installed on the delivery side of a pump station. These cases have stored energy immediately downstream of the non-return valves, which almost instantaneously reverse flow at the pump when a pump stops. And 3. Whenever a single pump stops and there are other parallel pumps in the station which continue to run. This is a very common scenario where the high head generated by the running pumps is almost instantaneously imposed on the stop pump. Let's take a few moments to understand what is happening when a pump's non-return valve closes. To examine what happens, let me use an example simulation. The example is a simple pump station with two pumps operating in parallel. Here we see the station running with both pumps on and each pump delivering about 7.5 litres per second. The pump station is fitted with a pressurized air vessel on the delivery side. As a result, the stored energy in the air vessel will rapidly decelerate the water in the pump station's delivery manifold when a pump stops. This example demonstrates the consequences of a very normal, frequent operational event. Pump number 2 is going to stop under automatic control while pump number 1 continues to run. Remembering that all non-return valves take a finite time to close, there will be a short period of time when pump number 1 recirculates part of its output back through pump number 2 before the non-return valve closes on pump number 2. A series of graphs that trace the water velocity through the non-return valve on pump number 2 will reveal what happens. That is here. At the same time, additional graphs will show the surge heads generated at 2 points in the pump station. One on the suction side of pump number 2, here, and the other on the delivery side of both pumps, here. First, we look at what happens if pump number 2 non-return valve is perfect and shuts with a closure time of 0 seconds. That is, the valve closes as soon as the water velocity reaches 0. Note, in all of these graphs, we are looking at very short periods of time, in this case, 2 seconds long. Pump number 2 stops at this point in time, here. In all of these graphs, the pump stops at the 0.1 second time mark on the graph. The water decelerates rapidly and reaches 0 velocity over about 0.1 seconds. That's a 0.58 metre per second change in velocity over 0.1 second is a deceleration rate of 4.8 metres per second squared. What happens to head at the suction side of pump number 2? Well, here we see a relatively modest 5 metre increase in head, up to about 10.5 metres, and the lowest the head drops to is about 3 metres. Now, what happens to head at the delivery side of the pump station? Here I can see the head drops briefly by about 7 metres, rises at most by about 2 metres, and will eventually stabilise about 3 metres lower. Conclusion: with a perfect non-return valve that prevents any reverse velocity, all looks good. No massive surge amplitudes and no extreme maximum or minimum heads. Perfect non-return valves are great. Everyone wants an inexpensive one. Where can we buy one? We can't. We can only buy realistic valves. I will come back to this subject later. To unfold the story a bit more, let's look at the other extreme, the total absence of a non-return valve, or a valve that closes so slowly that it is totally useless. Here we are looking at a graph of the velocity through the pump number 2 non-return valve, assuming it takes more than 8 seconds to close. The point of this graph is to reveal the magnitude of the system's ability to generate reverse flow through pump number 2. Here I can see the maximum reverse velocity would be about 1.7 meters per second, and it would occur at about 0.8 seconds after the pump stopped. That is a 2.2 meter per second change in velocity over 0.7 seconds, which is a deceleration rate of approximately 3.1 meters per second squared. This graph tells us that if left uncontrolled, pump number 1 would continue to recirculate a reverse flow of about 1.4 meters per second through pump number 2. Here we are looking at the potential of this system to generate reverse velocity for the scenario of one pump stopping and the other pump continuing to operate. Note that it is the water system that governs the maximum deceleration and potential reverse velocity through a non-return valve. The non-return valve itself is just a device that responds to this characteristic of the water system. The time that it takes a non-return valve to close after the water has reached zero velocity is governed by the mechanical design of the valve. Let's move on to unfold the story further. I'm going to change the closure time of the non-return valve on pump number 2 and look at the graphs of velocity and surge heads on the suction and delivery side of the pump. I'm going to look at 3 different closure times: 1 second, which is a relatively slow valve, 0.25 seconds, and then 0.1 second, which are both very fast closing valves. First, a sluggish 1 second closure time valve. In the 1 second of time it takes the non-return valve to close, the system has generated its maximum reverse velocity. Consequently, this valve slams shut with a reverse velocity of about 1.7 meters per second. On the pump suction, this causes the head to drop to vapor pressure repeatedly, and subsequently at one point creates a head spike as high as 110 meters. We are looking at a situation likely to cause cavitation damage in the suction pipework. On the pump delivery side, the valve slam generates a maximum head spike of about 285 meters. Depending on the pressure rating of all the pipework and fittings on the delivery side of the station, this spike may or may not exceed the maximum allowable operating head. For pump set number 2, this means a harsh set of temporary loads. About 300 meters head differential across the non-return valve, vapor formation and collapse in the suction manifold. This is a recipe likely to grow a list of maintenance tasks over time for valves, pumps, pipe and pipe fittings. Can we solve this problem by swapping over to a much faster non-return valve? Let's find out by looking at a valve that can close in 0.25 seconds. And I chose that value by trial and error, seeking a valve that would limit the maximum reverse velocity to 1 meters per second. Here on the pump suction we see that vaporization still occurs. However, the maximum head spike has been lowered to 65 meters. I won't waste time looking at the delivery head because the 0.25 second closure case has not solved the problem adequately. Even an extremely fast acting valve closing in 0.1 seconds will find itself closing against a reverse velocity of 0.6 meters per second in this system. And these velocity blips indicate that transients in the system briefly make the valve flutter open and closed. On the pump suction side, vaporization still occurs. The maximum head spike has been further reduced to 37 meters. On the pump delivery side, the valve slam generates a much lower maximum head spike of about 175 meters. Still not perfection, yet it might be in the range of acceptable loads on the valves, piping and fittings from a pressure rating and maintenance perspective. Whether it is acceptable or not will depend on the client's mechanical design standards. Key messages to take away from this lesson are the importance of firstly evaluating the system's potential to generate reverse velocities through the pumps. Secondly, evaluating the consequences of safe operating heads being exceeded or life of the asset being reduced if the non-return valves cannot close at the pace required by the system.